All right, welcome functions, folks. This is the lesson on describing functions. This is going to be a bit of a strange one. The 3-minute review is a little bit longer. I would like you to try for sure 1, 2, and 3. 4 and 5 we will go through together fairly carefully, but 1, 2, and 3 will go fairly fast through. And of course, if there's anything that you're not sure of, we can talk about in class. And then there's actually an activity. So, need to find some scissors at some point. I'll give you that hint. And a piece of paper that I think you got in class, along with this sheet itself should be a piece of paper that you printed in class, or you got handed to you in class that you didn't have to print at home. So a little bit of a different lesson today. All right, so pause the video and try at least 1, 2, and 3 of the 3-minute review, and then I'm taking it up right away. All right, there's the first couple answers, and I make mistakes in these videos. I realize that, and you can make fun of me in class if you like, but the whole idea here is in function notation, whatever goes there, the x goes in the same spots as it did in the function notation, right? So where there was an x, now there's an x minus 3. So I take out the x and I put in what x got replaced by, and then I've got some work to do, right? So this is x squared minus 6x plus 9 plus 3x minus 9, and I collect some like terms there. Those are like terms, and I get x squared minus 3x. It's a little bit of a coincidence there. You see some absolute value review. That should have been no problem, just a calculator exercise. The new and important, because our textbook uses it almost exclusively, is this idea of interval notation rather than set notation. So in grade 11, you learn how to describe sets of numbers, domains and ranges mostly, using this top stuff, set notation. Our textbook uses something called interval notation. It's a little bit shorter, I think. It's so most textbooks do this sort of thing. Unfortunately, it can often look like, kind of looks like a point. It just takes some getting used to. So in interval notation, the square brackets means for you to include the endpoint, and the round brackets means for you to don't include the endpoint. Notice if we're talking about a number line that goes off to infinity, we actually write the infinity in there, and it can never be equal to infinity. So that's why we use a round bracket instead of a square bracket. And hopefully you got the rest of those answers the same as me. And again, if you're having trouble with interval notation, you can ask about that in class. It'll come up again and again and again, and it'll be just something that we get used to in class and using our textbook. All right, so number 4 is actually where we're going to start the lesson, sort of, even though it's in the 3-minute review. State the domain and range of the graph to the right. Use set and interval notation. And I'm actually going to do something about absolute value too. So the domain, by the way, this thing's called an ellipse. It's kind of like a stretched circle. And we can see that it fails the vertical line test. This is not a function. Its domain are these values, right? There's the domain right there. -2 to 2 inclusive. So the set notation is -2 is less than or equal to x is less than or equal to 2. The interval notation would be, because we're including the endpoints, square brackets, -2 to 2. And then the range are just these values from -5 to 5. So the range, -5 to 5. And then in interval notation, even though this is a little bit strange because we usually think of intervals talking about x values, the y values in interval notation would be very similar, just like that. Sometimes we put in things like that to show that it's y is a member of this interval, and that's all good. The extra thing that I want to mention here is it says more absolute value. How has this got anything to do with absolute value? Well, the domain here, these blue numbers, are basically anything, all the numbers x whose bigness is less than 2. Right? From -2 to 2 is any numbers whose bigness is less than 2. So how do I say that in absolute value notation? Numbers whose bigness is less than or equal to 2. And that describes all the numbers that are between -2 and 2. This notation is kind of like a shortcut. And so what would be the similar one for range? Well, you give it a go. But it's all the y values whose bigness is less than 5, right? Y values whose bigness is less than 5. Notice that it would be incorrect to say bigness is less than -5 because the bigness of a number is never going to be negative. So that's incorrect. This is correct, and it implies the same thing that we wrote here in red for the range. All right, onwards. More absolute value. So then on a number line, we want to graph all the numbers whose bigness, right, absolute value, we think of as bigness. Bigness is greater than 3. So I'm doing a number line here. Not going to need many, but we're going to need negatives as well. What numbers have a bigness greater than 3? Well, certainly 4 does, and 5, and 6, and so on. But we got to worry about more than just integers, right? So like 3.1 is in there, and 3.11, and 3.01, 001, 3.00001 is close to 3 as we can get. So how we show that, remember, is with an open dot, an open circle, and then all these numbers. So this is x is greater than 3. But numbers whose bigness is greater than 3, there's negatives allowed as well. -4 has a bigness that's greater than 3. Right? So I also have this number. X is less than -3. And in fact, this statement implies these two pieces. And that comes both from the function that we learned yesterday and also from the definition of absolute value. These things make sense and are true. Okay. Long 3-minute review, like a 10-minute 3-minute review. All right. Next, this is a bit of fun, I hope. Math's always fun, right? So the first thing is you need to cut out these cards. All right, you got these cards cut out like this, and if you haven't done that, you got to pause the video and cut them out. Cut out your cards. And then we're going to do a little activity, you and I, sitting here at the computer. It'll seem a little bit silly, but I think it'll be good, clean fun. All right, now that you got your cards cut out, and if you didn't get your cards cut out, then you can pause the video until you do. What I want you to do is sort these into cards that have a domain of x's all real numbers and a pile that has not. And again, you can pause the video and do that, and then I'll take it up. Is that what your piles look like? All right. What's true about the functions that are left out? What's true about these ones? Well, as it says here, there's a restricted operation. If I take the square root, I can't take the square root of any negatives. So that's why x can't be all real numbers, because x can't be negatives. Taking the square root is a restricted operation. Same thing as taking the reciprocal or dividing by x. I can't divide by 0. So there's a hole in this one where x can't be 0. Dividing by x is a restricted operation. This is called discontinuous. A continuous function is one where you can start on the left and trace right through. Don't draw on your cards now, you'll mess them up, without lifting your pen. See how I did that without lifting my pen? But here, if I were to draw along, I'd have to lift my pen so I could get to the other side. That's discontinuous. When you have to lift your pen That's a discontinuous function. All right, ready? Roll again. Again, pause. We want you to sort them into range that is greater than or equal to 0 or not. All right, got your piles? If not, pause, because I'm ready to unveil. That's what I had. What about this one? Should that not be over here? Well, remember, it gets really close to the y-axis and never quite touches it. Do you remember the name of that? It's an awesome math word called an asymptote, right? It has an asymptote. Asymptote. It's fun to say, asymptote. And then it never quite gets equal to 0. Y never quite gets equal to 0. So if we talked about the range of this function, its y is greater than 0, not greater than or equal to 0. So it's properly put in this one over here. Discussing the end behavior, we'll actually talk about this in quite some detail, but the idea is, how does the graph end? When x goes to negative infinity, what happens to y? Well, y gets close to 0, and this is actually a definition of an asymptote. When y gets close to negative infinity, or x gets close to negative infinity, y gets closer and closer to 0, but doesn't quite ever equal to it. So that's why its range is greater than 0. Notice on the other end, when x goes to positive infinity for this graph, going on, what happens to the outputs? Well, y goes off to positive infinity, and there's not much we can say about that. This one implies there's an asymptote. This one just implies it has that up shape that we're used to from the exponential graph. Okay, ready for another one? Sort them into ones that are always increasing and not. Ready? I'm going to unveil. Always increasing. So always going up. This idea of always increasing means kind of as we read from left to right, the graph is going uphill, uphill, uphill. Notice that some of these other graphs have spots where they are going uphill and spots where they're not. So let's choose one from the not pile, and we want to describe where it is increasing. So this is an interesting one. Where is it increasing? Well, the sine graph from there to there, right? It's going uphill from there to there. So it's increasing on, and you don't have to write this down if you don't want to. You're going to for the homework later. Increasing on, and in interval notation, it's not increasing right at negative 90, but at right close to negative 90, not equal to. From negative 90 to 90, it's increasing, and then again from 270 to, well, it has to go right through 360 for another 180, so that's what, 450, and so on, dot, dot, dot. It actually increases on an infinite number of intervals. Notice for some of these other ones, a little less interesting. This one increases on an easy interval, 0 to infinity. And notice this is, I'm using my interval notation rather than set notation. All right, ready for another sort? Symmetric in the y-axis. Symmetric in the y-axis. So that means if you're to have a graph, there's the y-axis. Whatever graph it is, it's the same when you flip it this way. Okay. Ready? I'm going to unveil. Just the two of them, and not these ones are not. These are called even functions. They're even functions because they're symmetric in the y-axis, and they have this property as well. F at x is equal to f at negative x. So for instance, whatever I had for a positive value over here, for instance, if I had positive 2, I have the same thing if I were to put in negative 2. 4 in both of those cases for the parabola, the basic parabola, even functions. So that might make you think, well, is there an odd function? There is. An odd function actually has these properties. And this is in your note. You don't have to write all this stuff down. An odd function is symmetric through the origin or flips in the x and y axis. So not just, some people would think an odd function would be just one that's symmetric down here, right? This flips down here, but it's not quite like that. The idea, it flips this way and this way. So it would have to look something like that. So the idea, if you have a point here, it's symmetric through the origin to here. Flip in the x-axis and y-axis. So which ones are this technique, or this characteristics? Odd. Notice they have the property of, this is the algebraic, and we'll talk more about the algebra in the lesson. F of x equals negative f. Which ones are? Well, see if you can pick them out. There's only a couple. All right, unveiling. Did you get those three? So notice that any point I pick on any of these graphs, if I were to go through the origin, I'd get to the graph on the other side, right? That's what it means to be symmetric through the origin. And an easier way for us to think of it is to flip it in both axes. Right? If I flip it in the x-axis, then it gets to this graph, and then I flip it here, then it becomes that other piece. It's almost like there's a little bit of a rotation of 180 degrees. We could think of it that way as well. And that's an odd function. And we'll actually see this algebraically. What this means is, when I have an input x, if I take the negative value, and then instead of going up to the same function value, that I go to the negative value, that I get the same thing. And that's algebraically the idea of the two flips, one in the x-axis and one in the y-axis. And notice there's some functions that are neither even nor odd. A bonus question, you might want to write this down because it is a bonus question. Is it possible to have a function that is both even and odd? So the idea is that it has to have this property and that property. Is it possible? And so the idea, if you write this up, whether it is possible, or if you find a function, keyword function, that works, then you can write that up and hand it in. I'm going to stop the video because the lesson's coming shortly and is on the rest of the handout that we've been using for the 3-minute review, and there's a couple of examples there that I'll try and go through quickly. Keep those cards handy. They will come in handy for not only the rest of today, but for this unit and later in the course as well, possibly. Okay, so I'm going to pause the video and pick it up in part 2 in just a moment.